back everyone to another day of surface integrals. This time around we're going to be upgrading, we're going to be talking about surface integrals over vector fields, right? So we're going to do not just scalar functions anymore, but vector fields now. So in this video, as usual, we're going to do the introduction, so I'm going to give you guys some definitions. I'm going to talk a little bit about oriented surfaces, right? We need the sense of orientation for surfaces. And this is similar to orientation for closed curves. We'll have orientations of surfaces. And this will be largely determined by the unit normal vector. And I'm going to give you even more definitions. So the claim is this section kind of models what we did in 16.2, right? Originally, we did line integrals for scalar functions, and then we moved into line integrals of vector fields. So we're going to do the same thing here, right? We did surface integrals over scalar functions, and now we're going to do surface integrals over vector fields. Okay, so to get started, we need a few definitions here. So first of all, S is called an oriented surface. And this is kind of a wishy-washy definition, but it'll work for us if it has two sides. So that is if you can kind of paint the sides of the surface two different colors. All right, so let me give you some examples of this because it's kind of strange that we're even making this definition. So some examples of oriented surfaces, right, would be stuff like planes, spheres, all of our quadric surfaces, and really pretty much any of the surfaces that we've really talked about so far. So let me show you an example, right? It has two sides, right? Which means that we can kind of color them in different colors. So I went ahead and I pulled up the Monroe 3D calc plotter, right? So I went ahead and I graphed a plane, for instance, right? A plane, we have a purple side, and then we have this green side, right? So it has two different sides to it. Likewise, really any other surface that we've more or less dealt with. So here's a kind of crazy one here. You can see this one's made out of purples and blues, and if you flip it upside down, we have more oranges and greens sort of deal. So this also has two sides to it. You know, it's essentially a sheet of paper. Has two different sides, or kind of any of our quadric surfaces. So here's an elliptical paraboloid. So we have this kind of blue side, blues and purples here. And then on the inside of it, we have more greens and reds and stuff like this. So there's an inside and there's an outside, right? There's kind of these two sides to it. And so again, really everything that we know and love, right, is an oriented surface. And so it's kind of surprising that there are non-oriented surfaces. So I want to give you a few examples of those things. And so maybe the first one is something like a Mobius strip. Maybe you've heard of these or played with these. I'll go ahead and show you an example here in just a second. Another one would be like the Klein bottle. Klein bottle is a little bit interesting because really it belongs to 4 dimensions. Right, so in 4 dimensions, it doesn't actually self-intersect, but if you try to embed it in 3 dimensions, I mean, it still looks really cool, but it intersects itself, and so kind of it loses some of its, grandness. So let me go ahead. I'll show you an example of the Klein bottle here. I pulled up just, the Wikipedia page. So this is the Klein bottle, and the claim is if you were trying to maybe shade this thing, shade maybe in your favorite color possible, red, blue, green, whatever, kind of, it doesn't actually have two sides, right? Actually, you would end up coloring both sides red or both sides blue if you started to color, just one of the sides red or blue. So it's kind of remarkable that this thing doesn't have two sides. Another example is the Mobius strip, which I'll go ahead and show you how to make right now.
Welcome everyone. I'm going to show you how to make a Mobius strip, and then I claim that it only has one side. So I want to show you that it actually indeed does have only one side. I understand I'm cut off, but you won't need to see my face for the majority of this. So I'm going to go ahead and cut a nice strip of paper here to become our Mobius strip. Maybe you've made one of these before. And then I have some tape here. And instead of, making just a circle, right, which is where I would take these two strips and kind of put them together like this, and, I'd have a nice circle sort of deal, I'm going to go ahead and make a twist in here. So a twist. And then I'm going to go ahead and tape this together, and this is a Mobius strip. In fact, let me go ahead and do another piece of tape kind of on the back side here, which is a funny thing to say because really there's, again, only one side here. All right, so here is my nice Mobius strip. And now I'm going to go ahead and start coloring this. So I have this nice blue marker here, and I'm going to color this, and we're going to see what happens. So I'm going to go ahead and just start here, and I'm never really going to lift up the marker at all. I'm going to keep on coloring, 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 again, keep on coloring, keep on going, keep on going, keep on going. Again, never really lifting up the marker. And as I continue to color this, there we go. I just made it back, and we can see actually that I'm now coloring over the same stuff that I've already colored before. And as you kind of rotate this around, you can kind of see that I've colored blue on both sides of my Mobius strip. Again, really, there's not two sides to this thing. There's only one side because I never lifted up my marker. As I continued to color, I accidentally colored, both sides. So there's no way for me to color, one of the sides red and one of the sides green or something like this. You accidentally color both sides. And so this is a one-sided thing. It is not orientable, right? It's not an oriented surface.
All right, so assuming that we have, right, orientable surfaces, right, or an oriented surface, right, the claim is an orientation is just choosing one of the two sides. So we have some common orientations, right? You may see something like outward. And so you may hear the phrase, right, oriented outward. And this is for closed surfaces, which I'll define kind of below. You may also see upward, which means that it has a positive z component, right? So z is kind of the up and down. So if you want upward, you choose the positive z component. So, right, so in class, choosing an orientation comes down to selecting really a normal vector. So how you choose one of the two sides is by choosing a normal vector, because there are two normal vectors quite often, right? And these are going to refer to the two sides of a surface. All right. So one of the big theorems, right, the divergence theorem, will actually depend on these things, closed surfaces, right? And so I want to give you a few extra definitions kind of in preparation for the divergence theorem. All right, so first of all, a surface is considered closed, right? So we have closed curves, now we're doing closed surfaces, right? It's closed if it's the boundary of a solid region. So for instance, if we have a ball, right? So this is going to be like x squared plus y squared plus z squared is less than or equal to 1. So that's kind of, it's the sphere and all of the insides, right? So it's kind of everything inside of this, right? This is a nice 3D solid region. Now, if you consider just the surface, x squared plus y squared plus z squared equals 1, that's going to be just the surface of the sphere. Right, so it's just kind of this outer piece, the sphere. I don't know how to draw and kind of distinguish between the two, other than this one's solid over here, solid. And maybe you say that this one's, right, it's not solid, it's hollow or something like this, right? It's just the surface. Kind of think of like the balloon filled with some liquid versus just, the balloon itself, right? The actual surface of the balloon. So this is the boundary of some solid region. So that's how you get closed, and this kind of relates to, right, closed curves, right? Closed curves were the boundary of some region in the plane, in the xy plane, for instance. Finally, we have outward orientation is also referred to as positive orientation. So remember, kind of when we're talking about curves, something's positively oriented if it goes in the counterclockwise direction. Here, if we're talking about an orientation of surfaces, right, we call positive orientation the same thing as outward orientation. So you may see these kind of used interchangeably. All right, so now as I mentioned here, right, I have a little bit of a rant of why we need orientable surfaces, right? Why we need an oriented surface for the upcoming material. And it really has something to do with, right, we're going to be calculating out a surface integral over a vector field, right? So we're going to have a surface and we're going to have a vector field. And the idea is that we're going to count up, right? Kind of, you can imagine like particles moving through a surface. So if you have like a balloon, right, it slowly deflates, right? Kind of air travels through that surface of the balloon and kind of goes in this outward direction. So kind of similarly here, I have a very boring surface. I just have the xy plane here, and I have, this nice, it is an oriented surface, and I have a nice vector field, right? And you can kind of see that air would be escaping kind of upward, if these are kind of, maybe some force vectors or something like this. It will slowly escape through this surface kind of in these directions here, assuming that the surface is at all porous. And so you can see, again, the air is kind of escaping upwards, right? It's kind of going in this direction. But if you don't have an oriented surface, right, if it doesn't make sense to talk about, kind of the two sides, right, I would say that it's escaping through this yellow side right here. If it doesn't make sense to talk about these two sides, then again, kind of inward and outward, they don't make any sense, or upward and downward, right? It doesn't really make sense to talk about it if there's only one side to this surface. So you really need two sides in order to talk about what we're about to cover, which is really surface integrals over vector fields. So kind of all of the conditions, right, of what we're about to do is that you need some oriented surface. Otherwise, none of this really makes sense. And again, luckily, most of our surfaces out there, right, all of our favorite surfaces, they are all oriented. So we don't really have to worry. But there are kind of these crazy things out there in math, right? This is one of them. Non-oriented surfaces are these crazy things. They do exist, and we just won't be dealing with them when we're talking about surface integrals. Okay, so, and lastly, the last thing I have for us, right, is a few more definitions, and then we'll get some practice. So if you have a nice vector field, nice continuous vector field defined on an oriented surface, right, and suppose you have your favorite normal vector n, then the surface integral of f over our surface S. So this is going to be the surface integral of our vector field f dot, and it's this bold thing ds. So it's like a regular old ds, but now this s here is bolded. Okay, and this is going to be a dot product here. So what does this mean, right? This is notation, which means the surface integral of f dot n. So it's the normal vector here, and then this is the regular old ds that we had from our surface integrals over scalar functions, right? And in this case, right, once you take the dot product, you will have a scalar function. So then it's, right, just back our regular old surface integrals from last time. This integral is also called the flux. So hence the name here, the flux of f across S, right? I told here at the beginning, right, this is called the game of flux. So we are calculating out flux, which again, it's this notion of how much kind of travels through a surface. Okay, so finally, in order to help kind of calculate this out, it really helps to have a more concrete formula for our unit normal vector. So if our surface is given to us parametrically, then we can go ahead and rewrite this as the surface integral of f dot, and now we can express n, right, as this cross product between the tangent vectors. So I'm going to do r sub s cross r sub t, and now this may not be unit normal vector, so I'm going to go ahead and divide through by the magnitude, r sub s cross r sub t, and then we have to choose the orientation, right, because there's going to be there's two normal vectors, right, so you can do either the plus or the minus, right, and you're going to have to choose which orientation you'd like. And then this is going to be the regular old ds. So this is how we can express n if we have a surface defined parametrically. We can go ahead and reduce this down because we actually know this ds has one of these magnitudes of r sub s cross r sub t. And so this is just going to be the surface integral of f dot. And again, this is going to be a plus or minus, depending on which orientation you choose, r sub s cross r sub t. And then this ds has, again, one of these magnitudes of r sub s cross r sub t. And so this is just going to be dA, or if you'd like, dy dx, right? And then you can choose, wait, no, sorry, I misspoke there, right? So our variables here are s's and t's. So this dA is going to be really like a ds dt in this case. Let me go ahead and write that. That'll just be more clear. So I'm going to do ds dt. There we go. Because again, right, our surface is given to us parametrically. Right? So r depends on s's and t's. Okay. Likewise, if our surface is given to us explicitly, right? So we have some z as a function of x's and y's, then this flux integral right here is going to be the same thing as the integral over d of f dot. And again, we need kind of this unit normal vector here. we have to choose our orientation still, so we're going to have a plus and a minus, and then our vector here, right, for a nice explicit surface is going to be the partial of g with respect to x, the partial of g with respect to y, and then -1, right? This is back from chapter 14. It's been a while, right? And then normally you would divide through by this magnitude. We'd have the magnitude, or you'd have the square root of the partial of g with respect to x squared, the partial of g with respect to y squared, plus 1. But luckily, right, our ds here has exactly one of those, so that they're going to cancel, just like we saw before, and this is just going to be dA. And now that will be in terms of x's and y's. Ha! There we go. So again, the n in this explicit equation should look familiar from 14.4, right? That's where we first brought up this idea of tangent planes. And finally, right, these plus and minus signs are just determined by the surface's orientation. So this is going to be specified to us. So let's see an example. This will make a lot more sense as we start to compute some of these things. So we're going to go ahead and find the upward flux over a pretty boring surface, right? It's just z equals 2. It's going to be upward, right? So this is the orientation statement right here. So that's the orientation. And remember, upward means that it has a positive z component. Our surface is given explicitly, right? This is a function of x's and y's, even though there aren't any x's or y's, right? But there could be possibly x's or y's, but it solves z equals, right? So this is an explicit surface. And so let's go ahead and try to calculate out the upward flux, right? So upward flux, again, this integral right here is called the flux integral, and we've specified the orientation by saying the word upward. So I'm going to go ahead and calculate out the surface integral of f. Let me go ahead and enter in our specific x here, our f here. So this is x, y, and everywhere I see a z, I'm going to put 2, right? Because this is the restriction on our particular surface. So that's going to be 2. And then I'm going to dot with, remember this is what we're calculating out, so we're going to be dotting with plus or minus, and this is going to be the partial of our function, right? So this is from the surface. So again, this is the surface. In this case, we have this nice boring surface, z equals 2. So the partial with respect to x of 2 is just 0. The partial with respect to y is just 0. And then we have -1, then dA. So in this case, right, we have to choose between plus or minus. Well, if you want a positive z component, I'm going to choose the -1, right? Because minus -1 is going to be +1. So this is going to be the surface integral of x, y, 2 dot 0, 0, +1 dA. And so when you go ahead and you take that dot product, we're going to have, let's see, 0, 0, and 2. So this is going to be 2 dA, and we're over this region here, right? So we're over this region. And so, right, when I look at this region, I see that it's nicely integrated with respect to y and x. So I'm going to go ahead and choose, right, to go ahead and do dy dx. But I mean, if this was, better integrated with polar equations or something like this, you should use polar, right? So in this case, if I do dy dx, y is going to go from 0 to 1, x is going to go from 0 to 1. And so let's see, this is going to be the integral from 0 to 1, and if I integrate with respect to y, I'm going to get 2y, evaluate that from 0 to 1, dx. And so let's see, I'm going to have the integral from 0 to 1 of just 2 dx. And when I integrate that, I'm going to get 2x, evaluate that from 0 to 1. And so far, my final answer is just 2. All right, so there's our answer. The last thing I want to do is interpret that for us, right? So we have this nice plane, z equals 2. So it's the nice flat plane hovering above at z equals 2. So here at 2, right? And this surface integral, right, there's a vector field out there. There's a vector field out there, and I'm just going to draw maybe the vectors that lie on the surface. They're going to look something like this. And right, we did the upwards orientation. And so when you draw these vectors here, you can see that more are going upward than are going downwards, right? So more air is going through this upwards direction than in the downwards direction. And in fact, kind of it's all going in this upwards direction. at least in our region between 0 and 1, 0 and 1 for x's and y's. So I guess really I should just be looking at kind of this region right over here. So there's more kind of going upward through the plane than there is going downward through the plane, right? And it's by, this factor of 2 here. So that's what this integral is giving us, kind of is more of the vector field traveling through the plane in the upward direction or in the downward direction. And so when we choose this positive orientation, that means that we're counting how much is going positively through this plane, and in this case, 2. And because this is, greater than 0, that means more is traveling in this positive z direction than is traveling in this negative z direction. All right, so that's what this is giving us. I'll see you guys in class. We'll be doing a lot more of these problems. See you then.